In this video, I'm going to introduce you to one of the two most important crowning achievements of the calculus we've been working on. We are going to talk about Stokes' theorem. We have been doing a huge amount of work with calculus in 3 dimensions, and at this point, we have all the tools we need to put it all to work. The divergence, the curl, and surface integrals can all be combined to give us a couple of new theorems that are some of the most brilliant and elegant things that come out of calculus. In this video, we'll look at the first of these theorems, which is basically just a 3-dimensional version of the circulation form of Green's theorem. It's called Stokes' theorem. I want to do a quick review of Green's theorem. In the circulation form of Green's theorem, we started with a closed, simple, smooth, oriented curve C in the xy plane, and this curve enclosed a region R and a vector field given by f is equal to a vector with components fg, which is differentiable on R. The integral form of the circulation form of Green's theorem gave us the closed integral over C of f dotted with dr is equal to the double integral over R of g sub x minus f sub y dA, where the left side is the circulation along the boundary of R, and the right side is the curl of the vector field over all the points in R. Now, if I imagine vector fields as fluid flows, this tells me that the cumulative rotation of the flow within R is equal to the circulation along the boundary. So now let's look at Stokes' theorem. In Stokes' theorem, our plane region R in Green's theorem becomes an oriented surface S in R3. The circulation integral in Green's theorem is still a circulation integral in Stokes' theorem, but now it's a circulation over the closed, simple, smooth, oriented curve that forms the boundary of the surface S. In Green's theorem, I have a planar region R that is bounded by the curve C that has an orientation, typically taken to be counterclockwise as the positive orientation. The circulation form of Green's theorem for this region is the closed integral over C of f dotted with dr, which was equal to the double integral over R of del cross f dotted with k dA. Now we're taking it into R3 space, where I now have a closed, simple, smooth, oriented curve that forms the boundary of my surface S in the XYZ space. My closed integral over C of f dotted with dr in R3 space becomes the double integral over S of del cross f dotted with n ds. Now, keep in mind that the orientation of the surface has to be consistent for all points on the surface, and we choose an orientation based on the choice of direction of normal vectors. To help us with that, we use a right-hand rule that relates the orientation of S and C and gives us a method for choosing our orientation. With the right hand oriented so that the index fingers curl in the positive direction around C, the right thumb will generally point in the direction of the normal vectors. For all curves C with a counterclockwise orientation as viewed from above, the vectors normal to S will point upward. So the formal definition of Stokes' theorem is when I let S be a smooth oriented surface in R3 with a smooth closed boundary C whose orientation is consistent with that of S. We're going to assume that my vector field F is given by a vector with components f, g, h, and that it is a vector field whose components have continuous first partial derivatives on the surface S. Then the closed integral over C of f dotted with dr is equal to the double integral over S of del crossed with f dotted with n ds, where n is the unit vector normal to S determined by the orientation of S. I want to talk a little about interpreting Stokes' theorem. Stokes' theorem basically has the same meaning in R3 as Green's theorem has in R2. In the right conditions, the accumulated rotation of the vector field over the surface S is equal to the net circulation on the boundary of S. For a conservative vector fields on the domain D, there is a potential function phi such that F is equal to del phi. Since del cross del phi is equal to 0, we end up with del cross F is equal to 0, which means that the circulation integral is 0 on all closed curves in D for a conservative vector field. Because the circulation integral is also the work integral for the force field F, it also tells us that no work is done on moving an object along a closed path in a conservative force field. Let's look at an example. I want to verify that the line integral and the surface integral of Stokes' theorem are equal for the vector field given by F is equal to a vector with components 2z, negative 4x, and 3y, where S is the cap of a sphere with the equation x squared plus y squared plus z squared is equal to 169, above the plane z is equal to 12, and C is the boundary of S. The boundary is the intersection of the plane z is equal to 12 and the sphere x squared plus y squared plus z squared is equal to 169. In other words, x squared plus y squared plus 144 is equal to 169, which tells me that x squared plus y squared is equal to 25. So that C has the equation x squared plus y squared is equal to 25. X is equal to 5 cosine t, y is equal to 5 sine t, so that r of t is equal to a vector with components 5 cosine t, 5 sine t, and 12. And dr is equal to a vector with components negative 5 sine t, 5 cosine t, and 0. This tells me that my vector field F, given by a vector with components 2z, negative 4x, and 3y, becomes a vector with components 24, negative 20 cosine t, and 15 sine t. So that my closed integral over C of F dotted with dr becomes the integral from 0 to 2 pi of the vector with components 24, negative 20 cosine t, 15 sine t, dotted with a vector with components negative 5 sine t, 5 cosine t, and 0 dt. This gives me the integral from 0 to 2 pi of the quantity negative 120 times sine of t minus 100 cosine squared t plus 0 dt, which gives me negative 100 pi. Now I'm going to look at the surface integral. The surface sits over x squared plus y squared is equal to 25, and the normal to the sphere is given by a vector with components x over z, y over z, and 1. Del cross F is equal to a vector with components the partial with respect to x, the partial with respect to y, the partial with respect to z, crossed with a vector with components 2z, minus 4x, and 3y. This gives me a vector with components 3, 2, and negative 4. Since x squared plus y squared plus z squared is equal to 169, I can write that as r squared plus z squared is equal to 169. This gives me z is equal to the square root of 169 minus r squared, so that my double integral over S of del cross F dotted with n ds becomes a double integral over S of the vector with components 3, 2, negative 4 dotted with a vector with components x over z, y over z, and 1 ds. So that I get the double integral over S of the quantity 3r cosine theta over the square root of 169 minus r squared plus 2r sine theta over the square root of 169 minus r squared minus 4 ds becomes the iterated integral from 0 to 2 pi of the integral from 0 to 5 of the quantity 3r cosine theta over the square root of 169 minus r squared plus 2r sine theta over the square root of 169 minus r squared minus 4 r dr d theta. I do that integration and I get negative 100 pi, so that both of the integrals in Stokes' theorem are equal for my vector field on my surface S. Let's do another example. I want to evaluate the line integral that's given by the closed integral over C of f dotted with dr by evaluating the surface integral in Stokes' theorem with an appropriate choice of S. We're going to assume that C is oriented counterclockwise, and then we want to interpret our result. My vector field F is given by a vector with components 2xy sine z, x squared sine z, and x squared y cosine z, and C will be the boundary of the plane given by the equation z is equal to 8 minus 2x minus 4y in the first octant. I'm going to compute del cross F. This is equal to a vector with components the partial with respect to x, the partial with respect to y, and the partial with respect to z, crossed with my vector with components 2xy sine z, x squared sine z, x squared y cosine z, and when I do this cross product, I get 0. The surface integral is 0 here. This means that there is 0 flux across the plane and 0 circulation at the boundary. So now you get to try it. Pause the video and evaluate the line integral in Stokes' theorem to evaluate the surface integral given by the double integral over S of del cross F dotted with n dA. Assume that n points in the positive z direction. When you're ready, restart the video to check your understanding. Your field F is given by the vector r divided by the magnitude of r. S is the paraboloid given by the equation x is equal to 9 minus y squared minus z squared, where 0 is less than or equal to x, which is less than or equal to 9, but I'm excluding the base from this condition, and where r is equal to the vector with components x, y, and z. In order to evaluate this line integral, I need to work with my boundary. The boundary of the surface is the circle given by y squared plus z squared is equal to 9 in the yz plane. This tells me that r of t is given by a vector with components 0, 3 cosine t, 3 sine t, and that r prime of t is a vector with components 0, negative 3 sine t, 3 cosine t, dt. F is equal to the vector r over the magnitude of r is given by the vector with components x, y, z over the square root of x squared plus y squared plus z squared. In terms of the parameterized function, this can be written as the vector with components 0, 3 cosine t, 3 sine t divided by 3, which is equal to the vector with components 0, cosine t, sine t. So that my closed integral over c of f dotted with dr is the integral from 0 to 2 pi of the vector with components 0, cosine t, sine t, dotted with a vector with components 0, negative 3 sine t, 3 cosine t, dt. This becomes the integral from 0 to 2 pi of 0 minus 3 sine t cosine t plus 3 sine t cosine t dt, which is equal to 0. This is an introduction to Stokes' theorem. It's an extremely powerful theorem in calculus. Be sure and let me know if you have any questions.